Hello, everyone. Thanks for tuning in. My name's Alex Miltenberger, and today I'm going to be talking about some of my work that I've done with collaborators at Stanford University and at Lawrence Berkeley National Lab. So this work was motivated by a common problem in geophysics where you go out, collect your geophysical data, you come back, and your job is to interpret that geophysical data in terms of local geology or something that you might care about. But in this case, what we are finding is that we have a feature in our geophysical data in the circle here, which is a low conductivity zone or low resistivity zone. And when we want to see what that matches with in the geology, we have geologic cross-section. We see that there's no indication in the geologic cross-section that the that this low resistivity zone corresponds to anything. So this work is about how to reconcile those differences. We're interested in a fractured bedrock zone and ERT data. And so the study area that we're working with is in the headwaters of the Colorado River. So this is a mountainous watershed near the East River of Colorado, southwestern Colorado. Really well-studied area. A lot of DOE funded research has gone on in this watershed. And so we are focusing on a couple of different data sources. We have in this study area an electrical resistivity tomography survey and a couple of boreholes. And you can see some features around the study area like igneous intrusions, which are in red, and you also have a lot of faulting nearby as well. And there's also electric or airborne EM data in this area. And when you look at the airborne EM data, one of the big things that stands out is these linear features of low electrical resistivity. And we're calling these linear features, or this one linear feature, a fracture zone. And the reason we're calling it a fracture zone is because if you look at the two wells that correspond to this ERT survey line, we call them well A and well B. Well A, which goes right through this low electrical resistivity zone, has a lot more fractures in it than well B, which is outside of this low electrical resistivity zone. And so those fractures are helping more water get into the bedrock, which lowers the electrical resistivity, which is what we see in the airborne EM. But it also increases the hydraulic conductivity, potentially making this fracture zone a important subsurface flow pathway. So if we want to get a sense of what this fracture zone might be caused by, we can go back into the geologic history of the East River watershed. So we'll start at when the sediments that make up the watershed were deposited, which happened about 100 million years ago in what was called the Western Interior Seaway. So this seaway went through all of North America, right down the middle of it, and the East River watershed was on the western flank of this seaway. And the sediments were deposited mostly near shore marine environments in this seaway. But for that seaway to come into mountains that we see today, we had to experience the Laramide orogeny, which happened around 70 million years ago up until about 35 million years ago. And during that orogeny, that mountain building process, there were thrust faults and reverse faults in the East River watershed and around the region that were formed in response to compressional stresses from the orogeny. So then the orogeny ended, and the region entered a period with extensional stresses, and these extensional stresses persist until today. And as a result of the extensional stresses, both normal faults have opened up and reverse faults have possibly been reactivated. And the last process that may have influenced the formation of this fracture zone comes from glaciation. So over the past couple of million years, the glaciers have formed and receded. And when they receded, the stresses that they were impinging on the mountain or the valley sidewalls were released. And as a response to that release of stress, the mountains have actually started to essentially sag inwards to and create fissures along the mountain ridges that have been termed post-glacial tension fissures or Sakung fissures, different things along those lines. So each of these four processes that I outlined create a different hypothesis that may explain what this linear conductive fracture zone was caused by. So in the first hypothesis, we have some sort of bedding plane controlled fracture zone. So when perhaps a layer of sediment was deposited that became more conducive to fracturing, that fracture zone would be controlled by, or the morphology of that fracture zone would be controlled by the bedding planes. And then the second hypothesis is that thrust faults from the laramide orogeny actually created the fracture zone. And then the third hypothesis is that high angle normal or reverse faulting created the fracture zone. And the final hypothesis is that the fracture zone is from that post-glacial tension fissure. And so the main feature that that controls the differences in these hypotheses is the dip angle of the fracture zone. So different dip angles are going to indicate different origins of this fracture zone. So what we're is in testing which of these hypotheses based on the dip angle is most consistent with the geophysical data. And so the way we're going to do this is using a Popper-Bayes hypothesis testing framework. And it's a little bit different than what we've done so far, which is an inversion-based interpretation where we take the measured ERT data and then we invert for a lithology model and then interpret that lithology model based on our hypothetical or our hypotheses. And we can go a little bit deeper into this by using a Popper-Bayes hypothesis testing framework, where we actually start with our conceptual geologic models and then forward model ERT data, and then compare that forward modeled ERT data with the measured ERT data, and then compare, by comparing the forward modeled and the measured ERT data, actually seeing which hypothesis is most consistent with the measured data. So with any Bayesian framework, we need a prior model. So in this case, our prior model is pretty simple. We just assume a homogeneous background with constant resistivity, which we call rho B. Inside that background resistivity, we have a fracture zone resistivity, which is just this dipping layer. That resistivity of the fracture zone is rho F. That dipping layer has a thickness of H, a position of X naught, and a dip angle of phi. And then on the bottom, you can see a couple different realizations of the resistivity model from this prior model. Each of these parameters has their own uncertainties associated with them. So the bottom, you can get a sense of the different range of morphologies that we're considering with this prior model. Okay, so then an important question is, okay, we have this prior model. So what? Can we actually make ERT data that captures what we see in real life? So to do that, we're going to perform a prior falsification test. So on the left, you can see a couple of realizations from prior. You see two realizations. And then on the top right, you see the measured ERT data with the circle showing just the general region of where the ERT data has the conductive or feature that we're interested in. And so by performing dimension reduction using principal component analysis, we're able to see that the measured data, which is the yellow star, falls right within the prior model, which is the gray circles. So we can be confident that our prior model is capturing the important features in the ERT data that we're trying to understand. Okay, so we're good with our prior. We know it's working okay. And now what we need to do is actually predict the posterior distributions of the model parameters from the ERT data. So the way that we do that is we're going to train 5 random forest models. In the left, the random forest models are denoted in the gray boxes by the RF. And then once we have those 5 random forest models trained, we're going to use the measured ERT data, fit the measured ERT data right into all 5 of these random forest models to predict the 5 model parameters. And the way that those random forest models are going to work is based on these prediction plots, which are what you see on the right-hand side of this slide. So on the right-hand slide, the bottom axis is the true dip angle, the y-axis is the predicted dip angle, and the pink circles are the training set, and the blue squares are the test set. So we've split our prior realizations, which we have 2,000 of, into 1,000 train, 1,000 test. We train obviously on the train set, and then we apply it to the test set, and we're able to quantify the uncertainty in the random forest model using the test set. And the way that we quantify that uncertainty is by then putting in the measured ERT data, which is shown on the black line, the horizontal line, where we have a predicted ERT measured, or predicted dip angle from the measured ERT. And then by sampling true dip angles from along that black line, we're able to calculate a posterior distribution for the dip angle. So the blue histogram here shows the posterior distribution of the dip angle. And if you compare that to the prior, which is just that uniform distribution in the black line, then that prior, or then the uncertainty on the dip angle has been reduced by the measured ERT data when you go from the prior to the posterior. So it's more likely posterior, just the posterior, the true dip angle is somewhere a higher angle towards 90 degrees, or slightly off of 90 degrees compared to what the prior distribution was. So okay, we have that prior, or that posterior distribution of dip angle. Now we have to relate it to the different hypotheses. The way we do that is by defining likelihood functions for each for the dip angle given each hypothesis. Those likelihood functions are shown in the colored lines on this plot here. And then based on these likelihood models, we can actually calculate posterior probabilities. And what we see is that the bedding plane hypothesis and the thrust fault hypothesis have very low posterior probabilities, meaning that those hypotheses can be falsified. And this is important because we have 2 unfalsified hypotheses, each of which may have their own hydrogeologic impacts. So if you take, for example, the high angle faulting hypothesis on the left, you can imagine faulting implies some offset along that fault. So if you have, for example, a permeable sandstone layer, for example, shown in the blue on this slide, that permeable layer may be offset at the fault, and that would be an important feature to characterize to understand the hydrogeologic response to the subsurface structure. And on the right-hand figure, you can imagine the tension fissure hypothesis. That tension fissure may not actually extend much deeper than at most a few hundred meters deep. So if there's a bottom to this fracture zone, that would be an important feature to capture. And also, we would want to, because the fractures, the tension fissures are opening up from the top and filling in with sediment, we would also want to potentially look at what that sediment that's infilling the fracture zone would be doing to the hydrogeologic response of this watershed. So with that, I'll just wrap it up real quick. What we've done in this work is we've taken this resistivity from electrical resistivity tomography survey. And we've identified a discrepancy between the inverted resistivity and the geology, the local geology. And then we're able to identify what that discrepancy may be caused by testing 4 hypotheses that are related to the geologic history of the region. And we're able to show, using a combination of machine learning, Monte Carlo methods, and uncertainty quantification, that the normal reverse fault hypotheses and the tension fissure hypotheses are the most consistent with the geophysical data. So with that, I'm happy to open it up to any questions, and thanks for tuning in.